All right, so yesterday we were looking at how to balance equations. We are continuing with that process, but we're going to add looking at the different formats these equations are going to come in. So we're going to look at the four types of chemical reactions that we'll see with this. We'll continue to balance things, as I said before. You're going to want to have out the sheet from yesterday. Remember, I assigned 3 problems, so I want you to have that out. I also want you to have out the sheet that I passed out first, the one that says empirical molecular formulas at the top. It was the one that was out of 10. I'm going to look at question number 2 on there. There was a common mistake on that, and I want to make sure that we address that so that it doesn't, hopefully it doesn't continue happening or you don't get stuck on that again. So the opening question today was simply write a word equation and a balanced chemical equation for the reaction between hydrogen and oxygen to form water. So taking my prompt, turning it into a word equation, you would have had hydrogen, which if you wanted to note that hydrogen would be in gas form, you could have. Oxygen, could have noted it was gas as well. And then water is a liquid. And then putting the balanced equation in, you should have had 2H2 plus O2 reacts to form 2H2O. Remember that both hydrogen and oxygen are diatomic, so they're going to always be written with that subscript 2 when they're by themselves. All right. So going to the empirical molecular sheet with number 2. One of the issue that I saw, and it was kind of a common issue that it seemed to appear on several people's papers. So on this one, it says, what is the empirical formula for a compound that consists of 89.14% gold and 10.8 oxygen? So for the most part, people were fine here. This is number 2 on the empirical molecular sheet, the one that was out of 10. And so everybody was fine here for mass. Most people were fine with moles, where you divide by the molar mass. So you got a number like 0.4536 or 26. And then you got a number here like 0.6750. Where I was seeing the mistake is after you do your ratio and you come to your subscripts, you should have gotten a number that was like 1 and maybe like 1.49, which I rounded to 1.5. But a lot of people, because it was 1.49, just dropped the 49 off and put 1, and then said that my empirical formula was AUO. But remember, when in this position, when you get one that is a 0.5, we have to double everything. And then the other mistake I saw is some people would double this, but not double that. So coming through here, our true subscripts are going to be 2 and 3. So you get AU2O3. So the common mistake was forgetting about when you get a point something in a multiplier that it's not close enough to round, we have to either double it or quarter it or whatever. So look for that 0.5 and make sure you're doubling the 0.5s. And again, that was a mistake on several people's. So just make sure you're paying attention to that feature. All right. So yesterday I gave this out. Remember, this is going to be part of your notes. I don't ever want to see this turned in, but I assigned these 3 just for practice. Again, you can do as many as you want. I will probably look at a couple of more tomorrow. But just kind of going through here. So we just saw this one in our opening question. So to balance that one, we should have had 2H2 plus O2 forms 2 waters. For this next one, I have 2 aluminums here. I have 1 aluminum here. But I'm also noticing that I have 3 oxygens and 2 oxygens. I want to balance the oxygen first because that's going to affect my aluminum. So between 3 and 2, the lowest LCM or the lowest multiple between those is 6. So if I put a coefficient of 2 there, that makes that 6 oxygens. If I put a coefficient of 3 there, that makes that 6 oxygens. And so when I do that, I need 4 aluminums. All right. And then the last one down at the bottom, if you did it, or if you tried to do it without doubling it first, then you would have had an issue. So let me just show you what problems can happen, and it's always going to be ones with this format of the organic compound, this like C2H something compound. So if we start here and just try to balance it as it is, so I end up with, and I'm just going to show oxygen here, I end up with 2 oxygens on my reactant side, and on my product side I end up with 4 plus 3, I end up with 7. Well, the only number that can multiply by 2 to get to 7 would be 3.5, right? I can't have a coefficient of 3.5. I have to have all whole numbers. So what I would come through here is I would double everything. All right. So the correct coefficient should be 2, 7, 4, and 6 on that one. And like I said, tomorrow we'll look at this one, and this one. So those could be your next practices. All right. So recall from yesterday, when we're writing chemical equations, if we want to record the phase of a material, we can use these little annotations. So a lowercase s inside of parentheses tells us that it's a solid. Most of the time, if you have a metal or a transition metal that's by itself, it's going to be written as a solid, unless it's mercury, Hg. Then it would be a liquid. Really, anything that's written in black letters off of this periodic table, if it's by itself in a reaction, you could call it a solid. Liquids, you're going to have very few things that are liquids. Most of the time, so if we're looking, there's one diatomic that's a liquid, and that's bromine. But most of the time, the only other thing that we're ever going to really mark as a liquid is probably water. So don't get too hung up on liquids. Gases, Usually the gases that we mark will be common gases or like nitrogen, oxygen, fluorine, chlorine, anything written in red on the periodic table. And then remember those diatomics and things like that. Carbon dioxide, carbon monoxide will be gases a lot of times. All right, and then the other one that we introduced yesterday was aqueous. Remember, aqueous means it's dissolved in water. The compounds that you're usually going to see as aqueous are going to be mostly ionic compounds. However, there are some ionic compounds that are aqueous and some that are going to be listed as solids. And I'm going to teach that tomorrow. So, but aqueous is most of the time going to be ionic compounds. So that was just kind of a review of yesterday's, some of yesterday's material. All right. So I want you to go ahead and try to balance these three. All right. All right. So looking at the first one, we have H2 plus I2 reacting to form HI. In order to balance this, what coefficient do I have to add and where? Okay, so all I need to balance this one is a 2 in front of HI, and that balances it. So notice we have 2 hydrogens now and 2 iodines on both sides. All right. On the next one, we have sodium plus chlorine, and chlorine is Cl2 because it's diatomic, remember, and then it forms NaCl. So in order to fix this one, what coefficients do I need and where? All right, so I need a 2 in front of the Na, and I need a 2 where else? All right, so I need a 2 right there in front of NaCl, and I need a 2 in front of Na. All right, and that's going to give me 2 of everything. All right. And then we already kind of did this one somewhere, I think. But we have aluminum plus oxygen. That was one of the ones we did on the other one. Aluminum plus oxygen reacts to form aluminum oxide. So what subscripts do I need and where? All right. So I need, let me see if I did this right. All right, so I didn't do this right because that needed a 4. All right. And I'm going to back that one up because I was going to show you my thought process. All right. So if I started this and I just looked at it and I wasn't paying attention, and I started by putting a 2 in front of aluminum to balance out my aluminum, then I would notice that oxygen is out of balance. So I start trying to balance oxygen by putting a 3 there and a 2 there. Well, now I notice that aluminum is out of balance, so I can go back. Don't be afraid to change a coefficient that you did earlier if something else makes it change, is what I'm saying, what I was doing there. All right, so just kind of summarizing yesterday's stuff. Chemical equations are written to show the chemical change from reactants to products. I didn't mention this yesterday, but we've mentioned this in the past. Endothermic reactions absorb heat, so heat would be on the reactant side, or the energy would be on the reactant side. So yesterday we dealt with photosynthesis in our practices and all. Photosynthesis is endothermic. Cellular respiration, which is the reverse of that, is exothermic. So heat would be in the product side. Exothermic reactions, heat releases heat. It's a product. Remember that the mass of the reactants, the total mass of the reactants has to equal the total mass of the products, and that's from law of conservation. And then equations must be balanced so that the number of atoms of each element on each side of the equation are equal. So that's kind of our goal, is to get a point where we have the same number of atoms of each type on each side. Now, again, this is just a review thing from yesterday. Don't feel like you have to copy this down. It's all in our notes from yesterday. It was just, I wanted to kind of rehash that. All right, so moving into today's material. We are going to be talking about the types of chemical reactions. So when we look at chemical reactions, they're going to fall into a few set formats. So you might see a chemical reaction that looks something like this. Where two things come together to form one. You might see one that's the reverse of that, where one thing splits into two separate things. You might see one that's something like where you have a compound and a singular element, and it forms a new compound with a new element being by itself. Or you might find one where they basically trade partners. Let's do it like that. AD plus CB, something like that. And then there's going to be one last format that we're going to talk about, but it's special, and I'm going to kind of put it last, and you can't see that B. All right. So let's kind of look at these, and let's talk about these. So types of chemical reactions. There are four main types of chemical reactions that we're going to look at, and that occur between elements and compounds. Each of these types of chemical reactions follow a specific pattern or format, and I just kind of briefly went over those. But what this will help us with is if we can recognize the format, the type of reaction, we kind of can predict. If we're only given part of it, we can predict what's going to happen. So if you recognize that type, it can also help with balancing, because if you understand that if it's involved in ionic compounds, versus covalent and things like that, it will help. Aside from the fact that they're going to ask questions about it. All right. All right. So this actually is one of my favorite lessons to teach because y'all get to learn a little bit about my life and me as a high school student and things like that. So, and I kind of do it with stories and try to put some personality to these. So one of the things that you'll see me do when it comes to forming compounds and chemical reactions is sometimes I will almost talk about the elements as if they are people, because I'll put like emotions on them, like they want to hook up with this other element and things like that. So I'll kind of treat it like that today. So I just want y'all to be aware that I'm using metaphor. I am not saying that elements really care which element it hooks up with. I'm just trying to do that to make it a connection thing. All right. All right. Does everybody have what they need off of this page? All right. So the first type of reaction is called a synthesis reaction. All right. The word synthesis kind of means come together or to build or to produce. So I refer to a synthesis reaction as the dating equation. Wow. Let me fix something real quick. I think I was editing the slide and I must have hit something. All right. So the dating equation synthesis reaction, there's synthesis is sometimes called combination. I think in active, it shows you both names at the same time. It'll give you a choice of synthesis or combination. But the general format for a synthesis reaction is you have element A plus element B reacts to form compound AB. So the reason why I call this one the dating equation. So if we put this in terms of two students, we have student A and student B. And for whatever reason, maybe they're studying together, maybe they're just spending a lot of time together. Over time, they form an attraction for each other. And then eventually, they become inseparable and they become a compound. They become a couple. All right. So an example of in a real world example of this, I'm going to pull up in just a minute. But the kind of key thing to recognize a synthesis is you will only have one product. So a synthesis, you have two or more reactants, but one product. So the example of this is the one that we started off with this morning, is water, the formation of water. So I have 2H2 plus O2 reacts to form 2 molecules of water. So this is called the synthesis of water. Another one might be the formation of salt. So sodium plus chlorine. This is another one we did earlier. So we have a sodium atom and a chlorine molecule. They react to form sodium chloride, things like that. All right. So notice we had two different beginning points and they come together to make one thing. Iron rusting would be another example of this. So like you have a piece of iron like a nail, and it reacts with oxygen, and let's just say this was iron 2. So you end up with FeO. like that. So all of those would represent synthesis. All right. The second type of reaction is just the opposite. It's called decomposition. So in your experience, when something decomposes, what is it going to do? Break down. It's going to separate into smaller things. So when a piece of when a dead tree decomposes, it starts breaking down into smaller and smaller components. So in relationship terms, I call this one the bad breakup. Because if you look at it format wise, it's just the opposite of synthesis. So if we take a synthesis and flip it around, we get one thing, one compound, one molecule that breaks up into smaller parts. All right. And so in decomposition, the big thing is it's only going to have one reactant, and then it's going to have multiple products. So any of the synthesis reactions that I just showed you, we could flip around and break them apart. So another example would be decomposition of methane. So I have a molecule of methane, which is CH4, and it can be broken down into carbon and hydrogen. So again, if we have our couple that we created in the first scenario, they're going together for a while, and then all of a sudden one or the other gets the other person's phone and starts scrolling through it, finding things they don't like in the text messages, and then all of a sudden they break apart because they discover something they didn't want to see. All right. All right. All right. Does anybody need more time on this one? All right. So the next one, this is where it starts getting interesting. So single replacement. Single replacement. The word single is kind of key there because that means you're going to have one element by itself in the reaction. Sometimes instead of replacement, they will use the word displacement. Replacement and displacement kind of mean the same thing. It just depends on the perspective you're looking at this with. So in single replacement, used to call this one best friend stole my bay. That was a student wrote that on my slide one time, and I left it up there for years. So, but it's third wheel gets the girl. All right. So in this one, we have a compound and we have a singular element. And just putting it into the scenario, so we have our couple AB, and then we have whenever they're going out or whatever, B brings the best friend along. and the best friend's riding along in the car and all of that. And throughout the process of the night, A and C decides that they have a lot in common. So they're out, whatever, they go out to dinner or whatever, and eventually through the night, AC leaves together and leaves B wherever they were at. All right. So element or student C replaced student B in this relationship. And I guess they are no longer best friends. All right. All right. So when you're looking at these, notice that the reactions have a compound and a singular element. You will always have that format where you have something that's a compound and you'll have one that's by itself. And so in the example that I gave you, you have magnesium, which is a metal by itself, and it's reacting with hydrochloric acid. Magnesium has a greater attraction towards chlorine than hydrogen does. So if you put these two in proximity to each other, the magnesium is going to push out the hydrogen and replace it and become magnesium chloride, and then the hydrogen escapes as a gas. If you were paying attention yesterday in the reaction that we did yesterday, the demo that I showed you, I had sodium plus water, and it reacted to form sodium hydroxide plus hydrogen. Notice that that is also a single replacement reaction where the sodium replaced a hydrogen in that reaction. I didn't balance that one, but that should balance it, yeah. All right. But that was also a reaction. So displacement, one single element is going to replace another in a compound. This can happen and it's always going to involve ionics. And you could also have it to where it's like it could be the anion. It doesn't have to be the cation. So if I have something like, so if I have chlorine reacting with magnesium bromide, chlorine's a little bit more reactive than bromine. So chlorine will come and push bromine out. And so you end up with magnesium chloride plus bromine. All right. It doesn't have to happen. Doesn't have to just be the first element. It can be the second element as well. All right. All right. So this is the one where you get to hear a little bit about my life. All right. So double replacement. This is the prom trade-off. So prom's coming up in a couple of weeks. A little bit more, in a few weeks. So in this one, you have two compounds involved, and each compound is going to trade partners. So two elements in two different compounds will switch and replace one another. This will, most of the time, this will occur in an aqueous solution of ionic compounds. So, a little bit about me. I got to marry the girl next door. All right, and literally, my wife lived next door to me growing up. So we were really close friends. We never really dated. I went to a private school. She went to Destrehan. So all of that. But anyway, so it comes to her prom. I was dating one of her friends, and she was dating some guy. I didn't really know him that well, but my girlfriend knew him well, apparently. Anyway, we decide to double and get the limo and all of this. Now, understand, I'm a couple of years older than them, so I was already in college. I was working. I had money. They didn't. They were high schoolers. All right. So I paid for a lot of this. So I paid for the limo, all of this. So I'm just gonna throw some names out there. So A represents Amanda, who is my wife, and D represents Daniel, which is my name. All right. I'm gonna leave the other names out for protection of identity because some of you might be related to these people because they still live in St. Charles Parish. All right. Anyway, so we have Amanda and her boyfriend, and we have, we'll just call C Candace. All right. We have Candace and me. I want to know their name, not their last name. I'm not. All right. So I'm going to say Amanda was with Brian and I was with Candace. How about that? All right. So anyway, we decide to ride together. I pay for the limo. We went to Andrea's, which basically for the table, one person pays and they bring out multiple entrees. All right. Anyway, so we go through the night, all of that. Me and Amanda were talking because we had been neighbors forever. We had known each other forever. Candace and Brian seemed to have a lot in common. And they talked a lot. We end up going to prom, and at that time, Desterham was allowed to have proms, not there, but like in New Orleans and things like that. So we were at some reception hall in Fat City, is where the prom was, and we went there. Anyway, Brian and Candace disappeared on us, and we were together, so me and Amanda took the limo, went back home, and we have been together ever since. I'm not sure what happened with that relationship, but never really talked to either one of them again. So we traded partners, not in that sense, but I've been married so Amanda and I dated for 6 years after that, all the way through college, and then we got married right after college, and we've been together ever since, so like 25 years. So anyway, it worked out well for me because it got me out of a bad relationship that I didn't know about and gave us both a better one. Okay. Really? I know Candace became a St. Charles Parish police officer. I'm not real sure what happened to Brian. Candace wasn't very happy because Candace egged Amanda's car like the next week. Yeah. But that was like the next week after that happened. And then Brian, I just didn't know him, so like I didn't really care about him. What is Brian? I have no idea. Because some people like what they have, but they also like to have extra. Understand that I am not any longer, but my family had money, and so it was nice to ride around in the vehicles that I had and the things that I had and all of that. All right. So anyway, a real example of this. So we have sodium chloride, and then we have aluminum phosphate reacting. For whatever reason, sodium likes to be with phosphate more than aluminum does. So sodium replaces phosphate. And then because aluminum is now a free ion, it goes ahead and attaches to chlorine, which would have been a free ion, and they're together for a little while. Now, again, remember, anytime you see replacement, it could also be displacement. Now, understand the relationship between me and Amanda. We had been very close friends for a very long time, so it was perceived that we were dating even when we weren't. So don't think that there was total fidelity on both sides. Huh? From my freshman year till my sophomore year of college. So it had been for 5 years, 6 years. Now, even though I was a few years ahead of her in school, I graduated at 16. So she graduated at 17, 18, like the normal person. So I was a couple of grades ahead, even though I was the same age as them. So, because I started out at private schools, my parents put me in school early, and then I just stayed ahead. All right, last type of reaction is a combustion reaction. Combustion reaction is also referred to as redox sometimes, or oxidation reduction. But a combustion reaction has a very, very specific format. So notice all of the other ones I've been kind of generic, not using real elements. I've just been using like A, B, and C, D, and things like that. For combustion reaction, a combustion reaction is when elements or compounds are combined with oxygen. Yes. It's 4 main types. This is a special type. So I'm throwing this one in because you will see a question on this one. All right. So this, I guess, put this as a special type. If you want to say this is a 5th type, you can. But this is a special type. It kind of falls under the category of some other ones, though, that we can see. So like sometimes it can be a synthesis, sometimes it can be a double replacement, sometimes it's something in and of itself. But the key thing is oxygen always has to be present, and it always has to be part of the reactants. But another thing that has to be important on this is you have to have some compound that has carbon and hydrogen, oxygen in it. So it's always going to have an organic molecule in it. That CXHY is considered to be an organic compound. So that's always going to be present. So an organic compound burning with oxygen, and it reacts to form, and the products in these type of reactions, the products will always be carbon dioxide and water. So no matter what reaction, what combustion reaction happens, you're always going to have carbon dioxide and water produced. Let me see if I can fix that real quick. All right. I don't have a cute relationship story for this one. This one is just what it is. You have an organic compound. You have oxygen molecule. So in this one, the product of an organic combustion will always be carbon dioxide and water. wrap this up. So the types of reactions that we covered today, and even though I said there's four main types, there's the fifth subtype, which is combustion. So we have synthesis, which can also be called combination. Its generic format is A plus B reacts to form AB. Decomposition, which is AB reacts and it splits up and forms A plus B. Single displacement, which is A plus a compound like CB, and then your new compound is the A replaces the C. So you have AB plus C. Double displacement, where you have two ionic compounds and they trade partners. All right. So we have AB and CD, and then the new compound is going to be CB and AD. And then the last one is combustion. Combustion will always contain an organic compound and oxygen in the reactants. The products will always be carbon dioxide and water. Yes.
Like the test, is it going to show an example and be like, which type of thing is this?
Yeah. So it'll write a compound. Yeah. So it'll do something like this. So it'll give you sodium chloride plus aluminum bromide. And then it's going to show the reaction, and then it ends up being sodium bromide plus aluminum chloride. And so you would have to recognize which type that is. So this would be double displacement. If it showed something like this would be single replacement. So you just, and like I said, when I show the format like that, I'm just trying to give you the general thing. You know, if you had one that was sodium plus bromine, without even seeing the product, you know that this one is more than likely going to be synthesis. All right. And now, there is another type of combustion, but it's typically going to be called synthesis, where you have something like magnesium plus oxygen, and it becomes magnesium oxide. But that is synthesis as well. But if you're not given a choice of synthesis, it would probably be combustion, all right, because of the oxygen. Because by definition, combustion is just having to be oxygen. What I'm showing you is what's called organic combustion, and that's kind of more to it. Now, that's it for the notes. So in Chapter 7 active, we should be able to do problems 1 through 4, 20 through 26, number 31, and then 33 through 36. Sometimes they rearrange the problems. So if you get to one that looks like something we haven't covered, skip it, and then you can ask the question later, or maybe tomorrow's notes might cover it too. So just be kind of careful on those. But for the most part, we can answer those. I would start with the front ones first, like 1 through 4 and 20 through 26.